My name is Tianrui. I'm a first-year PhD student at UC Berkeley, advised by Krste Asanovic. And my first talk is on bringing this established technique called dynamic partial order reduction to hardware. So let's take a look at what really is partial order reduction for parallel software systems. So the premise is that you want to test parallel programs running on two different CPUs. I know there's a lot of constantly person here, so let's just zoom back from a software programmer's view. So you have basically two threads running on two different processors, and you can schedule these events in different ways. And you can see that in this case, when the thread 1 actually takes place between thread 2, and if you swap the order, the result stays the same. But however, if they write or read to the same memory address, then you swap their order, then the final order after the swaps actually changes. If with a more complex example, if you have multiple read and writes, regardless of your linearization between two different physical processors, the order within the same thread cannot be changed from a software perspective. So this is one linearization where you basically finish executing thread 1 on the first processor, then you start executing the next thread on the next processor. And in this linearization, the value of x is 3 and the value of y is 2 at the end of the execution. However, if you swap the order completely, then the value of x and y is also swapped. Only thread 1 in effect takes place. Here, if you further reorder the first write to x to the beginning, then you actually have a new result. That this reordering also brings a new result we haven't seen before. However, if you further swap the x and y's order, the result stays the same. And this is the observation for the partial order reduction for parallel software systems, is that you can have many different linearizations of the same two threads running on two different processors, but it will only introduce potential changes when you are in fact swapping a pair of operations that's operating on the same memory location. Otherwise, like this swap, it will not produce new results. The final results will still be the same, because there is in fact no race between the two transactions. And let's think about hardware with a similar mindset. So what's the state in this FIFO you can change, which is usually head pointer and tail pointer, and we can view them conceptually as a single finite state machine. And what are the possible operations on this RTL module? And on each side you can have a push or don't have a push. You can have a pop or not a pop. And if you do this, if you just do a simple static loop unrolling, you would have an exponential number of states you need to check against. However, there are potentially invisible states, which is this nice state. When you neither have a push nor a pop, then the state actually stays the same as your initial state. So you kind of reduce it from order 4 to an order 3. And actually this is duplicate. And actually the question is, beyond those invisible states, which are trivial to just prune away in our stimulus generator, can we merge the state further across different steps? For example, you can see that if two pops happen, then the final result should be the same rather than having them checked twice. So here we first generalize this for hardware ignoring clocks, and we can view each action on an interface as it kind of depends on some states that it will happen, and it will mutate some other state after the transaction successfully happens. And the insight here is the same because as you do with software, you don't reorder transactions that kind of have that doesn't conflict with each other, that doesn't read the element the other modifies. However, there's a slight complication, which is a lot of modern hardware are synchronous. That means they have clocks, and this is actually a new order between two operations, because now you don't have you no longer have a single linearization between two threads. Like, things can happen in parallel instead of mutually exclusive. So now we need to think about how do we generalize this for hardware. And the idea here is that by generating your stimulus in a way that doesn't have that doesn't create combinatorial dependency, you can actually still regard the same operation, even though they happen at the same clock cycle, as two distinct operations and reorder them the same way. However, the other complication here is that once you reorder, you in physical hardware, things are still happening in the interface you're looking at. So you also need to generate new action as place fillers for these new empty slots you created. And so the idea here is that all transactions are equal, but some transactions are more equal than the others. So you would try to pick the transactions that could potentially introduce more state changes, thus leading to bugs. So the idea is that instead of statically using the formal technique, using to calculate them, which we discovered doesn't really scale well because you can have many interfaces in parallel with many FSMs, and that just flows up extremely quickly, even if you have this state reduction technique. We actually use the delta of states between transactions as the proxy model for how basically how likely a transaction is to introduce bugs. So the idea here is that in addition to your old transaction generation techniques, in addition to your old transaction reordering techniques, when you are filling those points, you generate them based on a lookup table where you use the transaction and state tuple, where you use the pair to index into a dictionary probability, and you basically sample what are the next transaction to generate based on this probability. And here's our architecture. So basically, you will have some warm-up tests that are sanity tests, and then when you launch them on simulators, you record all the state transitions and all the things that needs to create that probability distribution. And the nice thing about this is that everything is in pure Verilog and a little DPI, so that your existing verification infrastructure can just run on the side. So the case may come that some other external verification collateral got triggered, and then you perform the reduction and the reordering. Then you sample from the probability distribution a new transaction to put there, and periodically it enters a cooldown to basically reset the probability to a uniform distribution to get out of local minimum. And yeah, this is basically our work right now. So one thing we'd like to do is to use a parser to extract dependency between interfaces and FSMs. We currently annotate them by hand, which is a little inefficient. And the other thing is we want to use systemc as top to drive the verification collateral, because CocoTB is a little too slow. And we also we have performed some evaluation against prior partial order reduction techniques, but we want to have some better evaluation compared between the current work and some fuzzing-based approaches like RFuzz. So with that,